Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 2 of a unit Nuclei. Let's begin with today's class. In today's class we are going to discuss about the mass energy. So when we say mass energy, we understood that the alpha particle consists of two protons and two neutrons, and the mass of the actual particle should be, it's a 4.0015 unit. So the total mass of the individual particle is the 4.0320 units, and the difference in the above two masses is due to the binding energy of the alpha particle. That is what we call as the binding energy, which is equals to delta m into c square. So for the alpha particle, delta m is it's a minus of 0.0305 unit, and this E binding would be equals to minus of 28.4 MeV. So the alpha particle has a lower energy than a collection of separated protons and neutrons. Since the protons in the nucleus are the charged particles, they have a potential energy associated with them, and this is much larger than the energies that is associated with electrons, molecules and chemical reactions. So the electric potential energy of protons in a nucleus is of the order of mega electron volt, and the potential energy associated with the strong force is negative, and it is also of the order of mega electron volt. So this is very large as compared to the typical atomic scale energies of the around 10 eV. The rest energy of the proton and neutrons can be found from E, that is equals to mc square. So the rest energy of the proton, it's a 938 MeV, or mass can be expressed in unit of energy per c square, that is equals to mass of the proton could be equals to 938 mega electron volt per c square. Mass can also be expressed in atomic mass units, such as the 1 atomic mass unit is equals to 1.676 into 10 to the power minus of 27 kg, or it is equals to 931.5 MeV per c square. Let's discuss the principle of equivalence. And according to the principle of equivalence that has been proposed by the Einstein, the energy equivalent of mass can be given as this is E equals to m into c square, and this mass equivalent of energy could be given as m, which is equals to ratio of E to the c square. And to estimate the binding energy of the nucleus, we can use this principle of equivalence to estimate the energy released in any nuclear reaction. That is what we also called as the Q value. We can use this principle of equivalence. Let's look at certain quick questions. The principle of equivalence is being used to estimate the binding energy of the nucleus. Yes. To estimate the energy released in a nuclear reaction. Yes. So both A and B, this should be the correct answer. Next, 1 atomic mass unit is equals to, it's a 1.66 into 10 to the power minus of 27 kg. Now let's discuss about the mass defect and the binding energy. So first, let's discuss nuclear binding energy. For any stable nuclei, the mass of a nucleus containing n neutrons and z protons is less than the total number of n isolated neutrons plus z isolated protons. This energy equivalent of mass defect is what we call as the binding energy of the nucleus, and this binding energy can be found by finding the mass number of nucleons and then subtracting the mass of the same number of isolated protons and neutrons. So the mass of the nucleus is always less than the sum of the mass of the constituent nucleons in their free state, and this difference in the mass is what we call as the delta m. So the binding energy of a nucleus can be given as, this binding energy would be equals to delta m into c square, where delta m is the mass defect and c is the velocity of light. If you want to calculate the binding energy in the arcs, then it's a delta m in the gram multiplied by 9 into 10 to the power 20. A binding energy in the joules, it's a delta m in kilogram multiplied by 9 into 10 to the power 16. And if mass defect delta m is in the atomic mass unit, then binding energy would be equals to, it's a 931.5 MeV. So if Z and A respectively represents atomic numbers and mass number of a nucleus, then the binding energy of the nucleus can be given as, look at this, this is equals to ZMP plus A minus Z multiplied by mass of neutron minus of M nucleus. This complete bracket, this complete bracket will give me the mass defect, which is what we call as a delta M into c square. So this is binding energy, which is equals to delta m into c square. This c square could be replaced by 931.5 MeV, where mp, this is the mass of the proton, mn, it is the mass of the neutron, and m, it is the mass of the stable nuclei. If someone asks me what is the binding energy per nucleon, then I can have the relation, it's a binding energy plus total atomic mass. If someone asks about the packing fraction, this is equals to m minus a divided by a, which is equals to delta m divided by a, where m, capital M is the atomic weight and capital A is the atomic mass in AMU. So if the packing fraction is negative, then the nucleus is more stable, and if the packing fraction is positive, then the nucleus is unstable. And if we talk about the 6C12, yes, carbons, then packing fraction for the 6C12 is the 0. Let's discuss about the binding energy curve. Yes, on the y-axis we are having binding energy per nucleon, and on the x-axis we are having the mass number. So this is the curve that is obtained on plotting the binding energy for nucleon versus mass number, is known as the binding energy curve. And as you can see this, that from approximately this region to this region approximately, it is constant. For lower elements, when I say lower elements, I'm talking about the mass. Yes, for lower elements the binding energy per nucleon is very less, even it starts on decreasing like this, even for the heavier elements. Yes, so binding energy per nucleon, or even we can say it's a binding energy, is high in the range of atomic number that is less than 28 to the, it is greater than 138. Light nuclei such as the hydrogen is combined to form very heavy nucleus for greater stability, and this process is what we call as the nuclear fusion. A heavy nuclei, when we say it's an A greater than 220, are highly unstable, and they are going to break into two nearly equal nuclei which is stable, and this process is what we call as the nuclear fission. So the most stable nuclei are those with the largest binding energy. They are nearly iron or nickel with approximately A equals to 56. So with increase in mass number, binding energy per nucleon first increases rapidly and reaches the maximum value for Fe56. The maximum value of binding energy per nucleon is about 8.8 MeV. Please keep this in mind and please remember this. Several examinations has asked this. Thereafter, with increase of mass number, binding energy per nucleon decreases very slowly and to about 7.6 MeV for uranium-238. And very light nuclei are least stable, and even very heavy nuclei are unstable. So the nuclei with intermediate mass numbers are the one which are most stable. So the decrease in binding energy per nucleon for heavy nuclei is due to the electrostatic repulsion. It is due to the electrostatic repulsion between the protons. And binding energy per nucleon for helium nucleus is about 7 MeV. If A is much greater than 56, then nuclear fission is possible with the release of energy. And if A is less than 20, the nuclear fusion is possible with the release of energy. And the nuclear energy is released in fission because binding energy per nucleon is greater for fission fragments than the initial heavy nucleus. So minimas are associated with nuclei containing an odd number of protons and neutrons such as 1h3 or 5b10 or 7n14, and the maximas are associated with the nuclei having an even number of protons and neutrons such as the 2he4 or 6c12 or 8 or 16 and something like this. So in the nuclear fusion process, energy is released because binding energy of the heavy nuclei formed as the result of fusion is greater than the total binding energy of lighter nuclei which are fused. So this is the reason why in the fission process and in the fusion process energy is being released. So look at this one more time. Iron whose binding energy per nucleon stands maximum at 8.7 MeV is the most stable and will undergo neither fission nor fusion. Yes, because it is by default stable at all. Whatever the elements that process of fission or that process of fusion, they are making that process to become a stable. While iron is by default a stable, they are not required to go for the fission or fusion or something else. So let's look at the quick questions. The difference between mass of the nucleus and total mass of its constituents is what we call as the mass defect. That is what we call as a delta M. Yes, this is correct answer. Second, if M is the atomic weight and A is the mass number, then M minus A by A represents, yes, it represents the packing fraction. I hope this is clear. Is it clear? Any doubts up till now? Is there anything? No? Great. Now let's discuss the forces that acts inside the nucleus. So basically we have this forces and that is what we call as the forces inside the nucleus. We have the nuclear forces, we have the Coulomb forces, we have the tensor forces, and we have the hardcore repulsive forces too. So let's begin our discussion with the Coulomb force. Basically it is the electrostatic force of repulsion between a proton and a proton, and this forces are responsible for instability of the nucleus. So as atomic number increases, Coulomb's force increases and the stability of the nucleus decreases. So we can say that 6c12 is stable because it is having the less number of protons, and when protons number is less, you understand this force is directly proportional to the product of these two charges. It's a q1 into q2. So as number of protons is less, their repulsive force would be less. But let's look at this. This is uranium 92U235. Yes, its number of protons is 92 in its stable condition. Yes, so as number of protons increases, our repulsive force will increases, and that can create an instability within the nucleus. Next, let's discuss about the nuclear forces. They are the forces which are acting within the nucleus or among the nucleons. That is what we call as the nuclear forces. And the nuclear force is much stronger than the Coulomb force, or we can say it is much stronger than the gravitational force. And the nuclear force between two nucleons fall rapidly to zero as the distance is more than the femtometers, and this leads to the saturation of the forces. So potential energy between two nucleus as a function of distance, and it is minimum at distance, what we call as the R naught. So we can say that repulsive force between proton is about 10 to the power 36 times as great as the gravitational force between them. And the ratios of relative strengths of the gravitational, electrical and nuclear forces is 1 is to 10 to the power 36 is to 10 to the power 38. Please keep this in mind, this has been asked too. Let's discuss the properties of nuclear forces. These forces are very strong, attractive forces. They are in fact the strongest force in the nature. These forces are charge independent. That means a force that acts, I mean a nuclear force that acts between proton, it is same as the force that acts between the neutron. It is the same that is act between the proton and neutron. It is very short range force. So nuclear forces are applicable only when the separation of the nucleus is of the order of 10 to the power minus of 15 meter. It is spin dependent forces. So nuclear force is strongest if the spin of the nucleons are parallel, and it is non-central force. That means the nuclear force does not act along the line joining the center of the nucleons. Properties of nuclear forces: they are the non-electrical, they are the non-gravitational forces, they are the exchange forces. That means when we say the mediating particles, that nuclear forces is due to the exchange of the pi mesons between the nucleons, and the certain pi mesons that we call pi plus or pi minus or pi naught was predicted by Yukawa. Yes, so it could have a certain variation like this. Yes, and the nuclear forces will show the properties of saturation. Let's discuss about the hardcore repulsive forces. So if the distance between two nucleons becomes less than 0.5 Fermi, then there exists a force of repulsion instead of force of attraction, and these forces are called as the hardcore repulsive forces. A nucleon does not interact with all other nucleons, but it only with a limited number of them which are nearest to it, and these forces are the strong repulsive forces, and these forces keep the volume and density of the nucleons constant. I hope this is clear. Is it clear? Is it? Great. Let's look at certain quick questions. Which of the following is not correct about the nuclear forces? They are short range electric forces, attractive forces. This is clear, correct. They are independent of the charges, correct. They change to repulsion at very close distance. This is clear. They obey inverse square law. No, this is incorrect. As I have been asked is not correct. This would be the answer because I have been asked incorrect one. I hope this is clear. Next, nuclear forces between two protons and a proton and a neutron, and between two neutrons are respectively FPP, FNP or FNN. Then yes, all these forces are equal because this force is charge independent. I hope this is clear. Is it clear? Great. So now let's wind up the session over here. This was all about the mass energy and the nuclear forces. Please go through this, revise it once, and this will be yours. As well as this is theoretical session almost. Yes, and that is being asked by our examinations. So please go through this. Please also go through the NCERT ones. This will make more concepts clear. Thank you. Have a good day. Take care. Bye bye.